All right, we are going to do 8.5 polar equations of conics, and this is a pretty interesting section because basically it takes what we've done with the three main types of conics, the parabolas, ellipses, and hyperbolas, and we talk about putting them into polar form, which we did in an earlier chapter. And so the first thing that the section does is it looks at this focused directrix definition of a conic section. Basically, that it makes this connection that a conic section is a set of all points in a plane whose distances from a particular point, called the focus, and a particular line, the directrix, in the plane, have a constant ratio. And so our focus is going to actually be in the same place that our normal focus is at for like a parabola or an ellipse or a hyperbola. And then we did talk about the directrix for a parabola, but now we're going to add that in as something we can have on ellipses and hyperbolas as well. And so some definitions here. The focal axis is the line passing through the focus and perpendicular to the directrix, and it's also a line of symmetry for the conic. The vertex, what we're going to use for the vertex here is the point or points where the conic intersects the axis. And that should work out to be the same as the vertexes that we had, the vertices, I'm sorry, that we had in our normal parabola, ellipse, hyperbola kind of situation. So to make this make a little more sense, look over here at the side. A parabola has one focus and one directrix. Ellipses and hyperbolas have basically two pairs. So maybe if I actually draw a picture over here of an ellipse, this could be horrible looking. But let's say this is our ellipse. Basically what's going to happen is we've got these two foci, and so what happens is we end up with a directrix over here, and we end up with the directrix over here. So that's basically what's going on. Same with a hyperbola. When we graph a hyperbola, the part without the boxes, okay, we end up with it looking maybe something like this. And so our focus on either side is over here and over here. So the directrix would be a line on this side. Okay, because we're talking about basically wherever our curve is. If I look at this picture over here, here's the focus, here's a point that's on my curve, and here's the line that goes to the directrix. Basically what we have is a constant ratio of from F to P, and then P to D. That is going to be, no matter where we move this point P, we'll have the same ratio of those distances. So down here at the bottom, we've got this focus directrix eccentricity relationship, and so basically that's what it's saying is the distance from P to F is going to go on top of our fraction. The distance from P to D would go on the bottom, and so if you actually find out what that is, that gives you the eccentricity E. And so we have this picture drawn like this, but maybe not obviously, but the easiest situation would actually normally be where our point that we're talking about is our vertex. And so that means that the distance from F to P ends up being this distance right here, and the distance from P to D ends up being this distance right here. So when we're looking at eccentricity, it actually will tell us with polar equations what type of graph we have. If it's greater than 1, we get a hyperbola. If it equals 1, it's a parabola. If it's less than 1, then it's an ellipse. And none of our e's should end up being negative. So an ellipse would be something between 0 and 1. So the next thing that we have are basically the standard formulas for our conics. And so these will actually end up giving us parabolas, ellipses, and hyperbolas. And so if it was an ellipse or a hyperbola, there would just be some more to our graph than what we're actually seeing. Just think of these as like just the part of our curve that's closest to the focus, and it could end up going out and becoming an ellipse or a hyperbola or whatever. So what the difference between these is like which direction it's opening, this curve is opening, and then the way we can actually basically easily tell which one of these to use is based on the equation of the directrix. Here on A, the directrix is x equals a positive number for k, and so that means that we're going to use this formula, which k is the number we have for the equation of the directrix. E is our eccentricity over 1 plus our eccentricity times cosine theta. Well, so if you can remember this pretty easily, because if x is a positive number for our directrix, then cosine and x go together, and this is a positive on the bottom. For part B, whenever we have a negative k for our directrix, we put in just that number k. We don't actually put the negative with it, if you notice. So like if our directrix is x equals negative 2, then k is 2, so we'd put a 2 up here. But since it's negative and it has x equals, it's going to be a minus sign and cosine on the bottom. Otherwise, it looks exactly like what this one was. Then down here, whenever we switch to opening up or down, we have y equals instead of x equals. So when y equals a positive number, that gives us a plus and a sign. And then whenever y equals negative k, it gives us a negative and a sign. So this is kind of the basic information we need to know. And then we'll end up working some problems with this. And here we go. Example 1, find a polar equation for the conic with a focus at the pole and the given eccentricity and directrix. Identify the conic and graph it. So if we want to start off here with A, we're actually going to do this a little bit out of order. We're going to identify the conic first because it's really easy. If E equals 5 over 4, that means E is greater than 1. Which means that we have a hyperbola. Okay, so we know we've got a hyperbola. Now we want to come up with the polar equation for the conic. So since x equals a positive 4, that means that the equation we're looking at has ke on top, because all of them do. On the bottom is going to be 1 plus e cosine theta. Okay, so we're going to plug in, because this is a positive 4, that means k equals 4. We know that e is 5/4. We're going to plug all this in and figure out what our answer is. So r equals k is 4, e is 5/4 over 1 plus 5/4 cosine theta. So we're going to simplify this. We want to get rid of all of our fractions that are inside of our fractions. And so basically this thing right here is what's going to cause our problem, because on top we can cancel out the 4's and we end up with just a 5 on top. But this on the bottom here, this 5/4, we want to make it go away. The way we're going to do that is we're going to times this fraction by this denominator, this 4 that's on the bottom of our bottom fraction. So 4 over 4, because we're multiplying by 4 over 4, so that means that we're really just multiplying by 1, which we're allowed to do. Well, what that's going to do is on top, we got rid of this 4 and this 4, so we're going to end up doing just 5 times 4, and we get 20 on top. On the bottom, we're going to distribute the 4, so we're going to do 1 times 4, which is 4, and then 5/4 times 4 gets rid of the 4 on the bottom and just makes that a 5 on the bottom. Cosine theta stays there. So this is our equation. Then we're going to plug this into our calculator and graph it. Okay, so we're going to graph this on our calculator. So what we need to do is go to mode, because we are doing polar graphing. I feel like we should be in radian mode. I'm pretty confident about that, actually, that we should be in radian mode. We want to be in POL. Oh no, that's a horrible, horrible error. Okay, I got polar back, so phew. So now we're gonna go to y equals. We're gonna clear out whatever's left from the last time we did polar stuff and type in this equation. Make sure that you put the bottom in parentheses unless you have a fancy calculator that can make it automatically go to the bottom of a fraction, and then do that instead. So 20 divided by 4 plus 5 cosine theta is in parentheses. Let's zoom standard and see what happens. Terrible, terrible things happened. This is supposed to be a hyperbola. Oh, this isn't really that bad. We just need to make our window bigger. We need to go more to the right. I don't really know how much. Let's try that. See, look, that's totally a hyperbola with the x in the middle for the asymptotes. So let's draw that on our paper. Ta-da! Look, there's our hyperbola. Let's do B now. Part B, E equals 1, so that's a parabola. And then we would look at this right here, y equals 2. That means that our formula we're going to use to start off with is going to be 1 plus e sine theta on the bottom because it's y equals and it's positive. So let's fill in. K is 2 because y equals 2. So r equals 2 times e is 1 over 1 plus e is 1 sine theta. So this is going to be r equals 2 over 1 plus sine theta. Type this in. This should be a parabola. We already said, so 2 divided by 1 plus sine theta. I feel like, okay, well that works. Maybe that window wasn't best, but this is a parabola that's opening down apparently. So, here we go. There's our parabola. Part C. E is 2/3, which means this is an ellipse because 2/3 is less than 1. Since x equals -5, we're going to use the formula ke over 1 minus e cosine theta. And if you're not sure where I'm getting those formulas, look at the slide right before this and look at your Directrix. Our Directrix here, x equals -5, that means that k equals +5. We don't take that negative with k. So r equals 5 times e, which is 2/3, over 1 minus e, which is 2/3 cosine theta. So what we're going to do here is we're going to go ahead and multiply this whole thing by 3/3 to get rid of our fractions. So r equals, we're going to end up canceling these 3's out, and we need to do 5 times 2 on top, which is 10. On the bottom, we're going to distribute the 3. So 1 times 3 is 3, minus 2/3 times 3 is 2. So 10 over 3 minus 2 cosine theta is our equation. We're going to type that in. I'm going to go ahead and zoom standard. And it just barely fits on there, but that works for me. Let's graph this ellipse. What did it look like again? There's our ellipse.